Hello and welcome to Unit 3, Lesson 12, which covers Newton's law of gravitation. In this lesson, we're going to learn how Newton discovered a universal law about gravity, that gravity works on every object that has mass and its attractive force between any two objects in the universe. And the common story about Newton is that he was sitting outside one day, he saw an apple fall to the earth, and that made him start thinking about the forces between the sun and the planets and other everyday objects. And he came up with an interesting theory. He theorized that the same force that makes apples fall to the earth, he calls this force gravity, also makes the planets and the moon follow their orbits, or elliptical orbits, as we learned in the last lesson. He figured out through experimentation that this gravity force varies with the inverse of the distance squared. This is sometimes called the inverse square law. So the further the two objects are apart, the weaker the force of gravity. And the force is inversely proportional to the square of the distance, or F is proportional to 1 over d squared, is one way to write that mathematically. He also figured out that the gravity force is proportional to the mass of each object. So if you have two objects, the more mass each one has, the greater the force of gravity, or the attractive force there is between the two objects. So he could put these two ideas together into one simple formula, which we call Newton's law of universal gravitation. And that law is written as a formula: F equals capital G times mass A times mass B divided by d squared, where MA and MB are two different masses for each object, and capital G is what we call the universal gravitation constant. Notice this is not the same as small g, which is 9.80 meters per second squared. That's the acceleration of gravity. Capital G is a universal constant. Now, Newton did not know what this number was. He knew that there had to be some proportional number in the formula, but he couldn't quite measure. He didn't have the technology to measure what this number was. Because gravity is an extremely weak force, it's hard to measure the force of gravity between smaller objects. So he was really unable to figure out what that number was. But about 100 years later, after Newton came up with his theory, there's a guy named Henry Cavendish. And he was a very good scientist, a very good, he was a chemist also, but he came up with a device that was very sensitive, and it was sensitive enough to measure the value of G that Newton predicted. And he did this experiment in the year 1798. And he came up with this apparatus that consists of a bar with two lead balls on the end of the bar hanging from a wire on the ceiling. And he knew that to make that bar spin a certain angle, or twist a certain angle, it required a torque on the wire. And he measured the amount of torque on the wire that would take to twist the bar through a certain angle. And then he fixed two larger masses close to the end of the lead balls, and those two masses created a force of gravity on the two smaller masses on the bar. And he was able to measure how much the bar twisted by using a mirror and a light on the mirror, and by measuring that amount of twist, he was able to calculate how much force there was between the two masses. And then working with the formula, he was able to calculate what the value of capital G is. Now this experiment, through this experiment, he determined the value of G, the gravitational constant, to be 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. So you notice the units work in the formula to cancel out meter squared and kilogram squared and leave you with a force of newtons. This experiment was called weighing the Earth because he was able to then use the value of G to calculate the mass of the Earth by taking the weight of everyday objects and using the value of G in the formula to figure out what the mass of the Earth must be. Let's do an example now of applying Newton's law of gravitation. If your mass is 85 kilograms and the mass of your desk is 24 kilograms, what is the gravitational force between you and your desk? Let's try this out. Do this with me on your handout there. So first of all, here's you, and here's your desk. You have a mass, your desk has a mass. So according to Newton's law, there's an attractive force between you and your desk. There's a force of attraction. You're pulling on the desk is pulling on you with the same exact force, equal and opposite forces. Remember that from Newton's third law. So let's use the formula for Newton's law of gravitation to figure out how much force there is between you and your desk. F equals G times M1 times M2 over the distance squared. So M1 is going to be your mass. We'll call M1 85 kilograms. And M2 is the mass of the desk, or 24 kilograms. Now the problem doesn't say the distance, so let's just assume a distance. Let's say you're very close to your desk. Let's say you're 1 centimeter from the desk, or 0.01 meters. Remember, distance has to be in meters when you put it in a formula. So we'll make that 0.01 meters. Now let's plug in our numbers and see what we get for our force. Now remember, the G, the gravitational constant, is 6.67 times 10 to the negative 11th. That was a number that was determined by Cavendish in his famous experiment. Multiply that by the mass, your mass, 85 kilograms, and then by the mass of the desk, or 24 kilograms, and then divide by the distance squared, or 0.01 meters squared. Punch those numbers into your calculator. You'll figure out that it's a pretty small force. Even 1 centimeter from your desk, the force is so small that you can't even feel it. The only force of gravity we can feel is the force of gravity from the Earth, because the Earth has so much mass. So you should come up with an answer of 1.4 times 10 to the negative 3 newtons. Or in normal notation, we would write that 0.0014 newtons. A very small force.